Section 1 Introduction. In this paper, we're diving into the fascinating world of large language models, LLMs, which are revolutionizing the field of artificial intelligence. Over the past few years, we've seen a surge in the development of models like GPT, PaLM, and Llama, which are all based on the decoder-only transformer variant. One of the key techniques used in working with these models is prompt engineering. This is a cost-effective method for tackling various tasks with LLMs. Essentially, we include the task description in the input we feed to the LLM. If we phrase this description correctly, the LLM can solve the task using its autoregressive token-based mechanism for generating text. These prompts can include example tasks with solutions, or even no example tasks at all. This mechanism has proven to be quite versatile, capable of solving a wide range of tasks that require mathematical, common sense, or symbolic reasoning. One approach to prompting, known as chain of thought, COT, involves including the intermediate steps of reasoning within the prompt. This has been shown to significantly enhance the problem-solving capabilities of LLMs without the need for any model updates. Building on COT, we have self-consistency with COT, COT-SC, a method where multiple COTs are generated, and the best one is chosen as the final result. More recently, we've seen the development of Tree of Thoughts, TOT, which models the LLM reasoning process as a tree. This allows for different paths of thought and introduces new capabilities like backtracking from non-promising outcomes. However, the TOT approach still has its limitations. It restricts the reasoning abilities within a prompt by imposing a rigid tree structure on the thought process. We believe that we can achieve more powerful prompting by allowing LLM thoughts to form a more complex, arbitrary graph structure. This idea is inspired by various phenomena such as human reasoning, brain structure, and algorithmic execution. For instance, when humans are working on a new idea, they don't just follow a chain of thoughts or try different separate ones. Instead, they form a complex network of thoughts. They might explore a certain line of reasoning, backtrack and start a new one, then realize that an idea from the previous chain could be combined with the current one, and merge them into a new solution. Similarly, our brains form complex networks with graph-like patterns. Algorithms also exhibit networked patterns, often represented by directed acyclic graphs. We believe that these graph-enabled transformations could lead to more powerful prompting when applied to LLM thoughts. To facilitate this, we propose the Graph of Thoughts (GoT) approach, which enhances LLM capabilities through networked reasoning. In GoT, an LLM thought is modeled as a vertex, while an edge represents a dependency between thoughts. This allows us to aggregate arbitrary thoughts by constructing vertices that have more than one incoming edge. However, implementing GoT presents several design challenges. For instance, we need to determine the best graph structure for different tasks and figure out how to aggregate thoughts to maximize accuracy and minimize cost. To address these issues, we've designed a modular architecture for implementing GoT. This architecture gives us fine-grained control over individual thoughts, allowing us to fully control the conversation with the LLM and apply advanced thought transformations. It can also be easily extended with new thought transformations, reasoning patterns, and LLM models, enabling rapid prototyping of new prompting ideas. We've tested GoT in several use cases, such as sorting, keyword counting for summaries, set operations, and document merging. Our evaluations show that GoT outperforms other schemes, particularly for tasks that can be broken down into smaller subtasks that are solved individually and then combined for a final solution. Finally, we propose a new metric for evaluating a prompting strategy, the volume of a thought. This metric helps us better understand the differences between prompting schemes. For a given thought, the volume is the number of LLM thoughts that could potentially contribute to it. We've found that GoT, by incorporating thought transformations like aggregation, enables thoughts to have significantly larger volumes than other schemes. Section Summary. Large language models, LLMs, like GPT and PaLM can be prompted to solve various tasks by including task descriptions in the input. Chain of thought, COT, and self-consistency with COT, COT-SC, have improved LLM's problem-solving abilities, but they still impose limitations. In this paper, the authors propose Graph of Thoughts, GoT, which models LLM reasoning as a graph, allowing for more complex thought patterns and transformations. GoT outperforms COT and COT-SC in tasks like sorting, while reducing costs, and enables arbitrary graph-based thought transformations within a prompt. Section 2 Background and Notation. Let's delve into some background information and terminology. We'll start with language models and in-context learning. When we interact with a language learning model, LLM, our conversation consists of our messages, which we'll call prompts, and the LLM's responses, which we'll refer to as thoughts. We use the standard notation to represent a pre-trained language model, LM, with parameters theta as p_theta. Lowercase letters like x, y, z, and so on, represent the thoughts of the LLM. We intentionally leave the definition of a single thought open-ended, allowing it to be tailored to specific use cases. So, a single thought could be a paragraph, like in an article summary, a document, as in document generation, a block of code, in code debugging or optimization, and so forth. Now, let's talk about different ways to prompt the LLM. First, we have the input-output (EO) method. This is a simple approach where we use the LLM to transform an input sequence X directly into the output Y without any intermediate thoughts. Second, we have the chain of thought (COT) method. Here, we introduce intermediate thoughts, denoted as A_1, A_2, and so on, between X and Y. This method has been found to significantly improve various LM tasks over the basic IO method, especially in areas like mathematical puzzles or general mathematical reasoning. Third, we can expand the COT method into multiple COTs. This involves generating several independent K-COTs and choosing the one with the best output based on a specific scoring metric. This method, known as self-consistency with COT, COT-SC, was introduced by Wang and colleagues. It improves upon the COT method by allowing exploration of different reasoning paths. However, it doesn't allow for local exploration within a path, such as backtracking. Finally, we have the tree of thoughts, TOT, method. This was independently introduced by Yao and Long, and has been used to some extent by other methods like thought decomposition. The TOT method improves upon COT-SC by modeling the reasoning process as a tree of thoughts. Each node in the tree represents a partial solution. From a given node, the thought generator constructs a certain number K of new nodes. Then, the state evaluator generates scores for each new node. Depending on the use case, the evaluation could be done using an LLM itself, or it could use human scores. The schedule for expanding the tree is determined by the search algorithm being used, such as breadth first search, BFS, or depth first search, DFS. Section Summary. In this section, the authors provide background information and notation for language models, LMs, and in-context learning. They introduce different prompting approaches, such as input-output, IO, chain of thought, COT, multiple COTs, and tree of thoughts, TOT, which enhance LM tasks by introducing intermediate thoughts or reasoning paths. These approaches allow for exploring different paths and constructing a tree of thoughts to model the reasoning process. Section 3. The GoT framework. Let's delve into the GoT framework, which we'll illustrate in a figure and compare with other prompting strategies. The GoT framework can be thought of as a four-part structure, consisting of the LLM reasoning process, potential thought transformations, an evaluator function for scoring thoughts, and a ranking function for selecting the most relevant thoughts. The LLM reasoning process is represented by a directed graph, where each point or vertex represents a solution to a problem. These solutions could be initial, intermediate, or final, and their form depends on the task at hand. For instance, in writing tasks, a vertex could represent a paragraph, while in sorting tasks, it could represent a sequence of numbers. The directed edges in the graph show how one thought has been used to construct another. In some cases, the vertices in the graph can belong to different categories. For instance, in writing tasks, some vertices might represent plans for writing a paragraph, while others represent the actual paragraphs. In such cases, we use a heterogeneous graph to model the LLM reasoning process, where each vertex is mapped to its respective class. To progress the LLM reasoning process, we apply transformations to the graph. For example, we might merge the highest scoring thoughts into a new one, or loop over a thought to improve it. These transformations go beyond those available in other models like COT, COT-SC, or TOT. The GoT framework also allows for new types of thought transformations, thanks to its graph-based model for reasoning. For instance, in writing tasks, we could combine several input articles into a coherent summary. In sorting tasks, we could merge several sorted subarrays of numbers into a final sorted array. Each transformation can be thought of as a function that modifies the graph, usually by adding new vertices and their incoming edges. The graph after the transformation is a combination of the original graph and the new vertices and edges, minus any vertices and edges that have been removed. To make the GoT framework as flexible as possible, we also allow the user to explicitly remove thoughts by specifying the corresponding vertices and edges to be removed. However, it's up to the user to ensure that the transformations are consistent. For example, the user shouldn't try to remove a vertex that doesn't exist. This feature allows for schemes where parts of the reasoning process that aren't likely to lead to improvements can be removed to save space. The specific form of the transformation and its impact on the graph depends on the specific transformation. We'll first explain the main graph-enabled thought transformations, and then describe how the GoT framework incorporates transformations from earlier models. Unless stated otherwise, we assume that no vertices or edges are being removed. Section Summary. The GoT framework is a tuple, G, T, E, R, where G represents the LLM reasoning process, T includes potential thought transformations, E is an evaluator function used to obtain thought scores, and R is a ranking function used to select relevant thoughts. The reasoning process is modeled as a directed graph G equals V, E, where vertices represent solutions and edges indicate the construction of thoughts. GoT enables novel transformations of thoughts using a graph-based model, allowing for aggregation and generation of coherent summaries or sorted arrays. Section: Aggregation Transformations. In the section titled Aggregation Transformations, the authors discuss the concept of the graph of thoughts, GoT, which allows us to combine various ideas into a single, more powerful one. This process is akin to merging different streams of thought, each represented by a vertex, into a single new vertex. This new vertex is then connected to the original vertices, forming a network of thoughts. This method is not limited to individual thoughts, it can also be used to aggregate longer chains of reasoning. Next, the authors introduce refining transformations. This process involves refining or modifying an existing thought, represented by a vertex. This is depicted as a loop in the graph, indicating that the thought has been iterated upon while maintaining its original connections. The third transformation discussed is generation transformations. This involves creating new thoughts based on an existing one. This process is similar to previous methods like TOT or COT-SC, where new vertices are generated from an existing vertex, forming new connections in the thought graph. In the section, Scoring and Ranking Thoughts, the authors explain how thoughts are evaluated and ranked. Each thought is given a score based on a general function that takes into account the thought itself and the state of the entire reasoning process. This scoring system allows for relative comparisons between thoughts. The authors also discuss a ranking function that returns the top-ranking thoughts based on their scores. The specific forms of these scoring and ranking functions can vary depending on the use case. For instance, in a sorting scenario, the score or rank might be determined by the number of elements correctly or incorrectly sorted. Section Summary. The aggregation transformations in GoT allow for combining and reinforcing the advantages of multiple thoughts while eliminating their disadvantages. This can be achieved by creating a new vertex that represents the merged thoughts and adding outgoing edges from the original thoughts to the new vertex. The refining transformations involve modifying the content of a current thought, while the generation transformations generate new thoughts based on an existing thought. Thoughts in GoT are scored and ranked using a general function that takes into account the state of the reasoning process, and the ranking function returns the highest scoring thoughts. Section 4: System Architecture and Extensibility. Let's delve into the structure and adaptability of our system. Our system, referred to as the GoT architecture, is composed of several interconnected modules, as shown in the figure, highlighted in blue. These modules include the prompter, which crafts messages for the LLM, the parser, which extracts information from the LLM's responses, the scoring module, which checks and rates the LLM's responses, and the controller, which oversees the entire reasoning process and determines how it should proceed. Within the controller, there are two key components: the graph of operations, GoO, and the graph reasoning state, GRS. The GoO is a fixed structure that outlines the graph breakdown of a specific task. In other words, it dictates the transformations that should be applied to the LLM's thoughts, along with their sequence and dependencies. On the other hand, the GRS is a dynamic structure that keeps track of the ongoing reasoning process of the LLM, including the history of its thoughts and their current states. Let's break down each module. 1. Prompter. This module is in charge of preparing the prompt to be sent to the LLM. It specifically handles encoding the graph structure within the prompt. The GoT architecture allows users to implement graph encoding specific to their use case by providing complete access to the graph structure. 2. Parser. This module is responsible for extracting information from the LLM's thoughts. For each thought, the parser creates a thought state, which contains the extracted information. This thought state is then used to update the GRS. 3. Scoring and validation. In this step, we check if a given thought from the LLM meets certain correctness conditions, and then assign it a score. The method of deriving the score may involve consulting the LLM. Depending on the use case, a human may also assign the score. For use cases like sorting, simple local scoring functions are used. 4. Controller. This module implements a specific strategy for selecting thoughts from the GRS structure. It also decides which transformations should be applied to which thoughts, and then passes this information to the prompter. Furthermore, it determines whether the entire process should be concluded or if the next round of interaction with the LLM should be initiated. In our current design, this decision is guided by the execution plan outlined in the GoO. Section Summary. The GoO architecture consists of several modules, including the prompter, parser, scoring module, and controller. The controller contains the graph of operations, GoO, and the graph reasoning state, GRS, which specify the task decomposition and maintain the ongoing reasoning process. The prompter encodes the graph structure within the prompt, while the parser extracts information from the LLM's thoughts and updates the GRS. The scoring module verifies thought correctness and assigns scores, and the controller selects thoughts and transformations, deciding when to finalize the process based on the execution plan specified in GoO. Section 4.5 GoO and GRS. In this section, we'll be discussing the graph of operations, GoO, and graph reasoning system, GRS. To start, let's imagine that you're building a GoO. This is essentially a blueprint for how your thought operations will be carried out. You only need to create this structure once, before you start executing your operations. Each operation within the GoO knows which operations come before and after it. As the GoO is executed, it keeps track of the ongoing reasoning process. It records which operations have been carried out, the status of all the thoughts generated, their validity, their scores, and any other relevant information. We've made sure to provide APIs that are easy to extend, making it simple to implement different prompting schemes. These APIs are highlighted in the green section of the figure in the documentation, where you'll also find detailed explanations. We've also included examples of prompts used by these operations and a corresponding GRS in the red section of the figure. Now, let's look at some examples of how the graph of thoughts, GoT, can be used. We'll focus on one use case due to space limitations, sorting. In this example, we're sorting numbers from 0 to 9, including duplicates. The language models we're considering struggle to sort a sequence of these numbers correctly beyond a certain length, especially when there are duplicate counts that don't match. To overcome this, we use a merge-based sorting method in GoT. First, we break down the input sequence of numbers into smaller subarrays. We then sort these subarrays individually before merging them into a final, sorted sequence. In this context, a thought generated by the language model is a sequence of sorted numbers. To evaluate the outcome, we compare the input sequence, represented as A1, A2, N, with the output sequence, represented as B1, B2, Bm. We calculate a score that reflects the extent of errors in the output. This score is the sum of two components, x and y. X represents the number of consecutive pairs of numbers that are sorted incorrectly. If two numbers, say I and I plus 1, are out of order, i.e., bi is greater than bi plus 1, then x increases by 1. If the numbers are sorted correctly, x remains the same. Y, on the other hand, measures how well the output sequence maintains the frequency of the numbers in the input sequence. For each number x, ranging from 0 to 9, we calculate the difference between the count of x in the input sequence and the count of x in the output sequence. If the output sequence perfectly preserves the frequency of x, y remains the same. Any deviation in the count increases y by 1. To make the score easier to interpret, we apply a clipping function to it, setting a maximum value equal to the length of the sequence, n. This is because some baselines can result in a large number of outliers with high error scores. Finally, to express the score in a positive way, we subtract the error score from n. This gives us a measure of how many elements are correctly sorted. Section Summary. The section describes the construction and execution of a graph of operations, GoO, instance, which serves as an execution plan for thought operations. The GoO maintains updated information about the reasoning process, including executed operations, generated thoughts, their validity and scores. The section also provides examples of prompts used by these operations and a corresponding graph of reasoning strategies, GRS. Additionally, a use case of sorting numbers is detailed, where the GoO employs merge-based sorting and calculates a score based on the correctness of sorting and preservation of frequency of numbers. Section 5.2 Set Operations. In this section, we'll be discussing set operations, with a particular focus on set intersection. This concept is widely applicable in various fields, from comparing genomes or documents to pattern matching. The process of finding the intersection of two sets is quite similar to sorting. We start by dividing the second set into smaller subsets. Then, we identify the common elements between these subsets and the first set, with the assistance of the language model, LLM. The intersecting elements are then combined to form the final result. To evaluate this process, we use sets of varying sizes 32, 64, and 128 elements. We also adjust the proportion of common elements in both sets, ranging from 25% to 75%. Our scoring system is based on the total number of elements that are either missing or incorrectly included in the final intersection. Let's denote the two input sets as A and B, each containing n elements, and the output set as C, containing m elements. The error scope is calculated as the sum of three components: the number of elements in C that shouldn't be there, the number of elements missing from C, and the number of duplicates in C. This is because the LLM represents the set as a list in natural language. To provide a positive score that reflects the accuracy of the computed elements, we subtract the error scope from n and take the maximum of this value in 0. Next, we'll discuss keyword counting, which is used to determine the frequency of specific keywords in a given category, such as countries in our example. The input text is divided into multiple sections, and the keywords in each section are counted. The sub-results are then combined. The number of sections can be adjusted or left to the LLM, which can treat each sentence as a separate section. To score this process, we first calculate the absolute difference between the computed count and the correct count for each keyword. These differences are then added together to get the final score. Section summary. Set operations, particularly set intersection, have various applications in fields like genome or document comparison and pattern matching. The intersection of two sets is implemented by splitting the second set into subsets and determining the intersection of those subsets with the first set using the LLM. The resulting intersection sets are then aggregated for the final results. In keyword counting, GoT splits the input text into passages, counts the keywords in each passage, and aggregates the sub-results. The score is calculated by summing the absolute differences between the computed keyword count and the correct count for each keyword. Section 5.4 Document Merging. In Section 5.4, we discuss the concept of document merging. This process involves creating a new non-disclosure agreement, NDA, by combining several existing ones. The aim is to minimize repetition and maximize the retention of information from the original documents. This method can be particularly useful in legal procedures where information from multiple sources needs to be consolidated into a single document. To evaluate the effectiveness of a merged document, we use the language model, LLM, to calculate two scores. The first score measures the redundancy of the document, with 10 indicating no redundancy and 0 suggesting that at least half of the information is repetitive. The second score assesses the retention of information, with 10 signifying complete retention and 0 indicating no retention. We then calculate the harmonic mean of these two scores to get the final evaluation. In Section 6, we discuss the latency-volume trade-off. We demonstrate that our method, GoT, improves upon previous methods in balancing latency, the number of steps required to reach a final thought, and volume, the number of preceding thoughts that could influence a given thought. We define the volume of a thought as the number of preceding thoughts that could potentially influence it. We assume that producing a single thought takes a constant amount of time and set the total cost for each method to be proportional to the number of thoughts. We compare three different methods: COT-SC, TOT, and GoT. COT-SC consists of multiple independent chains starting from a single thought. TOT is structured like a complete tree with a branching factor of k. GoT combines a complete tree with a mirrored version of itself, with the edges reversed. Our analysis shows that while COT provides a high volume, it also has high latency. COT-SC reduces both the latency and volume by a factor of k. TOT has low latency and volume. GoT is the only method that achieves both low latency and high volume. This is possible because GoT uses thought aggregations, allowing any intermediate thought to reach the final thought. Section summary. Document merging is a method to generate a new document by combining multiple input documents with overlapping content, aiming to minimize duplication and maximize information retention. It is useful in legal procedures and other scenarios where multiple sources need to be consolidated. The GoT prompting scheme improves the trade-off between latency, number of hops to reach a final thought, and volume, number of preceding thoughts that could have impacted a given thought, compared to previous schemes, achieving both low latency and high volume by leveraging aggregations of thoughts in the graph decomposition. Section 7 Evaluation. In this section, we'll be discussing the evaluation of our method, GoT, and how it compares to other existing methods. We'll primarily be comparing GoT to TOT, as TOT has been shown to outperform other methods consistently. However, we'll also include comparisons with IO, COT, and COT-SC for a more comprehensive analysis. We've chosen to leave out some data that doesn't provide any significant insights, such as the results from COT-SC. To evaluate these methods, we used 100 input samples for each task and comparison baseline. We set the temperature to 1.0 and used a 4K context unless stated otherwise. We also adjusted the number of thoughts in each scheme to ensure similar costs across all experiments. We conducted extensive experiments with the branching factor, K, and the number of levels, L, to ensure a fair comparison of GoT with cost-effective and advantageous configurations. We plotted two versions of TOT, one with a higher branching factor and lower depth, TOT, and another with a lower branching factor but higher number of levels, TOT2. We aimed to find a balance between having fewer generation rounds with more responses per round, which is more expensive, and having more rounds with fewer responses. We also experimented with different problem sizes, P, which in the context of sorting, refers to the number of numbers to be sorted. Due to budget constraints, we focused on using GPT 3.5 and GPT 4, and found that Llama 2 was generally less effective and slower to run. Our analysis showed that GoT outperforms all the considered baselines in terms of quality and reduces inference costs compared to TOT. GoT was able to improve upon TOT and TOT2 by a significant margin across all problem instances. While TOT generally had higher quality than TOT2, it also had much higher costs. GoT, on the other hand, always had lower costs than TOT and comparable costs to TOT2. For example, GoT was able to reduce the median error by approximately 62% for a problem size of 128 compared to TOT, while also reducing costs by more than 31%. This is largely due to GoT's ability to break down complex tasks into simpler subtasks, solve these subtasks independently, and then gradually combine these results into the final outcome. Compared to IO and COT, GoT consistently delivered much higher quality results. For instance, for a problem size of 64, GoT's median error was approximately 65% and 83% lower than COT and IO respectively. However, the costs of GoT and TOT were much higher than IO and COT. This is primarily because we didn't artificially increase the lengths of the chains of reasoning in COT if it didn't improve the results. Most importantly, GoT's advantages in quality increased for all baselines as the problem size increased. For example, in sorting, while GoT only slightly improved upon TOT2 for a problem size of 32, its median error count was approximately 61% lower for a problem size of 64 and approximately 69% lower for a problem size of 128. In conclusion, our analysis shows that GoT is indeed well suited for complex problem cases, as the execution schedules usually become more complex as the problem sizes increase. Section Summary. In the evaluation, we compare GoT to other state-of-the-art schemes such as TOT, IO, COT, and COT-SC. We use 100 input samples for each task and experiment with different parameters to ensure cost-effectiveness. The analysis shows that GoT consistently outperforms other schemes in terms of quality and reduces inference costs compared to TOT. It also performs better than IO and COT in terms of quality, although its costs are higher due to the multiple thoughts generated for each operation. Additionally, the advantages of GoT increase with the complexity of the tackled problems. Section 7.3 Discussion on Task Decomposition. Let's delve into the topic of task decomposition. When we break down a task into smaller subtasks, we effectively reduce the size of the responses and the input. However, the static part of the prompt, which includes a few examples, can sometimes become a significant overhead. But don't worry, we've noticed that these examples can often be trimmed down without losing their indicative value, which helps to further reduce the cost. Our ultimate aim with task decomposition is to simplify the task to such an extent that our language model can solve it most of the time with just a single prompt, or maybe a few additional steps. This approach significantly reduces the number of refinement steps needed later on. Plus, our results show that combining the results of these subtasks is usually easier than tackling a large task from the start. So, our language model often succeeds in piecing together the final solution. Now, let's look at some related work. We've detailed different prompting paradigms in a previous section. There's a wealth of research related to prompting, but we'll just touch on a few key ones here. For instance, Wang and colleagues proposed an approach called Plan and Solve, which adds a planning stage to enhance the chain of thought. Fu and team designed a method to improve prompting within a chain of thought using complexity-based criteria. The self-taught reasoner, or STAR, generates several chains of thought and picks the valid ones. Similarly, Shum and colleagues developed a method that generates a pool of chain of thought candidates and selects the best one based on its match with the ground truth and a policy gradient-based method. Automatic prompt generation addresses the scaling issues in the chain of thought. Joe and team suggest selecting the best prompt from a set of candidates. Lastly, in prompt chaining, different language models are cascaded, allowing for more powerful reasoning by prompting different models with different contexts. Our approach is different from these, as we focus on the capabilities of a single context. Section Summary. When decomposing a task into subtasks, the size of responses and input tokens decrease proportionally. However, the static part of the prompt, such as few-shot examples, can still be reduced in size, which helps decrease the overall cost. The goal is to break down the task to a point where the language model can solve it correctly most of the time using a single prompt, reducing the need for refinement steps. Additionally, combining sub-results is usually easier than solving large task instances from scratch, making the language model successful in aggregating the final solution. Section 8.2 Self-Reflection and Self-Evaluation. In this section, we'll delve into three key concepts: self-reflection and self-evaluation, language model planning, and the role of graphs in computing. Firstly, let's talk about self-reflection and self-evaluation. These are relatively new concepts that have been employed to improve various tasks, such as generating code or managing computer operations. In our graph of thoughts, GoO model, we use self-evaluation to a certain extent to make decisions about how to develop the thought graph within a given prompt. Next, we'll discuss language model planning. There's been a surge of research recently on how to use language models to plan complex tasks. Our GoO model can be viewed as a universal framework that could potentially enhance these planning methods by providing a new approach for creating intricate graph-based plans. Lastly, we'll explore the significance of graphs in computing. Graphs have become a crucial and widely used component in the world of computing. There's been an increasing interest in areas such as graph databases, graph pattern matching, graph streaming, and graph machine learning, including graph neural networks. The use of graphs has proven beneficial in numerous modern research fields. For instance, in social sciences, they're used to examine human interactions. In bioinformatics, they're used to analyze protein structures. In chemistry, they're used to design chemical compounds. They're also used in medicine for drug discovery, in cybersecurity to identify intruder machines, in healthcare to detect fraudulent claims, in web graph analysis to provide accurate search services, in entertainment services to predict movie popularity, in linguistics to model relationships between words, in transportation to find efficient routes, and in physics to understand phase transitions and critical phenomena, among others. In our work, we utilize the concept of graphs as a fundamental mechanism that enhances the ability of language models to generate prompts.